Continuing on with chapter 20, here is example problem 6.2. We have a cylinder piston setup that contains 1 liter of saturated liquid of R410A at 20 degrees Celsius, and the piston is now slowly expands, maintaining constant temperature to a final pressure of 400 kPa in a reversible process. Right, so it's constant temperature, so it's an isothermal process. Somehow we're able to, outside of the vapor dome, continue to be at a constant temperature. We want to calculate the work and the heat transfer required to accomplish this process. So we will start out here. I'll draw like a little picture of the thing. Okay, we want to recognize that here's the piston. We're dealing with this as being the system right here. So it's contained all the stuff that's inside here. And so in this process, and we could actually look on a PV diagram, helps us to see what's happening. It's going to get here at a constant pressure, right? Because during this portion of the thing, it's a constant temperature. So it has to be a constant right here as it's going from this phase to this phase. It just is the way that it's going to be. And then it starts to change down this is isothermal, so this is like a line of constant temperature on a PV diagram for this substance. On the TS diagram, it's going here straight across. So what we're doing here is we're going to have work out from this, and we're going to have heat in. And we can just tell that we're going to have that type of arrangement here. So we're going to take a look at table for B.4.1. And so for state 1, we know that it starts out as a saturated liquid. So that's what it tells us, that it's right there on that point right there. So we're going to look up at temperature 20 degrees Celsius, and I might as well work through it as we go through. Why not? I know it makes it for a longer video, but I think I would appreciate if people would actually work through the things themselves instead of just throwing numbers out at me. That's my opinion. All right, so let's see where we're at. We're at 20 degrees Celsius. So here you go, 20 degrees Celsius, positive is 1,444.2 kPa. And we'll go ahead and write down some of the things that we know. Okay, so amongst the things that we're given, so a clue right here, we're given the volume is 1 liter. So the volume at state 1 is going to be 0.001 cubic meters. Could look it up, see what the corresponding thing is. So maybe I should write down what the PSAT is, because we had just said it a second ago. And so that's 1,444.2 kilopascals. And as I was working through this problem, I actually wrote down a bunch of things, and I don't think I needed most of them. I do think I need to know this right here. So we need to know what the fluid specific volume is. That's going to give us the mass, because we might want to know, it doesn't say work per mass and heat per mass. It just wants the actual work, not a per mass basis. So we're going to want to have the mass, so we need this right here. So let's look up VF while we're here at 20 degrees. And that should be the fluid right there, right? So here's our fluid. Come down to here, and 0.000, so 3 zeros, 923. 3 zeros, 923. 0.123923 cubic meters per kilogram. And that's going to get us the mass. We could do that right away if we wanted to. Take the volume 1, divide it by VF1, if you will. And so 0.001 and 0.000293. That's how I make mistakes, is I flip numbers around all the time. and that comes out to 1.083 kilograms, right? We might also want to know, because of trying to see if we need anything from this. Yeah, we might also need U. Yeah, I think we need U of the fluid. Okay, and how do I know? I'll tell you this in a second. And then we also going to have, do we need S of the fluid? Yes, we need S of the fluid, right? We need this one to help us with the work. We need this one to help us with the heat exchange. It's an isothermal process, so, and we're going to do it slowly. So the slowly in the isothermal means it's going to be assumed to be a reversible process, and therefore we're going to be able to find what the area underneath this is going to be equal to the heat exchange of a TS diagram. It wouldn't be true unless it's in a reversible process. But so we need this S, and then once we get that heat, we'll be able to subtract out the U, because it's one group of stuff. Because remember the big picture, U2 minus U1 for a closed piece of a closed system like this is going to be Q1 to 2 minus work 1 to 2. So we'll be able to find work if we find heat and we find this change in U, right? So the UF is going to be right here under 20 degrees, right there. Should be this value, right? We're finding UF right here and finding that it is 87.94. 87.94 kilojoules per kilogram. And then for the fluid of the entropy for 20 degrees, we'll have 0.3357. 0.3357 kilojoules per kilogram degree Kelvin. All right, and so, okay, so we're going to come over to here to state 2, and it expands at a constant temperature to a final pressure of 400 kPa. So we want to try to find out all this information at 400 kPa. Fortunately for us, that's going to be superheated, right? So we have we know that to be true. Yeah, okay, well, we just might have to check, right? Let's see if 20 degrees is available in the superheat at 400. That's one way that we could approach it to find out. So 400 kPa, sure enough, 20 is in that range right there. So we have, we don't need this, but we could have been asked what the volume was. I'm sorry, right here. So we could work up out to see what that volume was. We have this right here. We're going to need that, and we're going to need this value right here. So 276, and we might even write down what the, no, that's fine, right there, okay. So 2 at P2 equals 400 kPa, and T2 is going to be still 20 degrees Celsius, right, because it's isothermal. So we'll find that we have a U2 is going to be equal to 276.44 kilojoules per kilogram, and an S2 is going to be 1.2108 kilojoules per kilogram degrees Kelvin. All right, that's the things that we just found from right 20 coming over to it's only 20 degrees. We say 20 degrees. Yeah, we said 20 degrees. Right. 276. We are at 1 point. Yep. Okay. So for the work or from let's see. I'm trying to think of how to say this and similar to here. So we could say that we have the S1 minus S2, and we say M times the things right there. So those are the little s's. And we got integral of Q over T from going from 1 to 2 onto the thing. But the t is constant, so we can bring that outside and multiply here. So q1 to 2 is going to be equal to m times t s2 minus s1. And therefore 1.083 times, and this is going to be 20 degrees plus 273. And then we're going to have, so 2 is, I'm going to say this correctly, I think 1.2108, and we're going to subtract out 0.3357. So we get a positive value, and that means that is heat in, right? If you had no other way of knowing. And so we get a positive 277.8 kilojoules. And then, as I mentioned up above here, we're going to have this rearranged so we could have that the work between 1 and 2 is going to equal Q12, and it's going to be plus U2 minus U1, or Q1 to 2 plus M times U2 minus U1. Right, so work 1 to 2 is going to equal 277.8 plus, oh wait, I might have got the signs wrong. Yeah, sorry. Well, let's be careful here. I did that wrong, sorry. So that should be, this is jumping over onto that side over there, so that should be minus this right there, right? Yeah. So get rid of that plus. Minus 1.083 is our mass from up above. And our U2, we found that to be 276.44. And then minus 87.94 up above. So U1 to 2 is going to be 73.65 kilojoules. So there you go. Here's the answer to that part right there. And you're going to use some of that in the logic that goes between each of the points when you're doing problem 1 on homework number 9. We'll continue with some more examples, but I'm not going to do the examples that I pulled from that other gentleman's video. I just posted the videos of those, so I'm not going to make my own videos of those examples. So I'll see you in the next one that's not included, if that makes any sense.